Hi there, welcome to your lesson on geometric sequences. Before talking about geometric sequences, it's important to go back and take a look at another important kind of sequence. Before looking at geometric sequences, it's important to look back at another type of sequence called an arithmetic sequence. Arithmetic sequence looks like this. We have a sequence of numbers with terms in it. Term 1, term 2, term 3, term 4, term 5. And we see as we follow the terms that each time you go from one term to the next, we're adding 3. Notice we're adding 3 every time. If we have a common difference or common addition or common subtraction of numbers between terms, we call that an arithmetic sequence. And then we call that common difference, that difference between terms, to be d value. In this case, it's 3. So with an arithmetic sequence, if we want to go from first term to second term, we can use what's called a rule like this. We have our u2, which is our second term. To get the second term, we begin with the first term and we add one common difference. And we can see that here. To get the second term, we began at u1 and we added the common difference once. We added 3 once to get to there. That's what this means. So what would this same equation be if we wrote it for u3? All right, to get to u3, we can begin at u2 and add the common difference once. Same thing we did here. So to get to the third term, we can begin at the second term, u2, and we add the common difference once. This is what's called a recursive rule. To write a rule like this, in order to find some term in the sequence, we need to know the previous term. However, it's often more useful to do what's called an explicit rule, which would look like this. Instead of doing this for u3, we can write it like this. To get the third term, we can still begin at the first term. So to get to the third one, we begin at the first term, but we do two jumps, 2 additions of the common difference. So to get to u3, we begin at u1 and we do 2 jumps of this common difference. Okay, so write a rule like this now for u4. To get u4, we can begin at u1 and do 1, 2, 3 jumps of the common difference. So to get to u4, start at u1 and then add the common difference 3 times. Notice for u5 we would have the same thing. Notice every time we have a term that we need, we do 1 less of the common difference here that we're adding, because the number of jumps is always 1 less than the term we're arriving at. So what would be a general rule? A general rule for that would then, if we want to get to any term in the sequence, un, we begin at u1 and we add the common difference n minus 1 times. This number means it's 1 less than this number, and we can see that here. This number is always 1 less than this. All right, that's arithmetic sequences. Let's take that understanding and take it further into geometric sequences. So here's a situation we begin with. If a single person always infects 2 others on one day, so let's say there's a virus going around. This is something we're not familiar with in our world for sure. Let's say one person can infect 2 people each day, and then they go into quarantine. Then how many would be infected after 64 days? So if this person didn't go into quarantine, then the next day they would infect more, and then the next third day they would infect more. But as soon as they infect 2, they realize, oh, I better go in quarantine, so they disappear. So now there's these 2 walking around, and they infect 2 people each. And then they go into quarantine, and then there's these people walking around, and so on and so on and so on. So we have the 1 person, then 2, then 4, then 8. Notice here we are not adding the same number each time. To go from 2 to 4, we added 2. But to go from 4 to 8, we added 4. So we're not adding 2 every time. So it's no longer arithmetic. This is what's called a geometric sequence. We're actually multiplying by 2 every time. To get from 1 to 2, we multiply by 2. And to get from this one to this one, we multiply by 2, and then also by 2. This comes from a very classic problem called the doubling problem. Please pause the video now, read the doubling problem history here, and then answer the question, what's wrong with the image that's given when you read this description here? Okay, you probably noticed that it says the number of grains of rice need to double each time. So we have 1, then 2, then this should be 4, and then, I don't know, here's 4, but then there's no 8, or maybe this is 8, I guess. Is this 8? Yeah, that looks good, and this is 16. Oh, maybe I was wrong. It looks like it's pretty good. All right, and then before you know it, there's so much rice the board can't handle it. Let's talk about how much that. There's 2 questions we're going to come back to in this unit. One is this: how would you be able to find out the number of grains of wheat on the last square of this chessboard? As you know, a chessboard is 8 by 8, so that means there's 64 squares. So eventually, the last square will be square 64. And how many grains of rice will there be? And then, what is the total number of grains of wheat or rice on the board? Wow, it would be a huge number. But let's talk about this first problem today. Okay, so here's a chessboard. Here is 2 to the power 0, 1 grain of rice on there. Anything to 0 is 1. 2 to the power 1, 2 grains of rice or wheat. 2 to the power 2 is 4. 2 to the power 3, 8, and so on and so on. We can keep going, and we can see a pattern. It's always 2 to some power. That's how we create a doubling situation. To get 1 to double to 2, to double to 4, double to 8, we have to have 2 to the power. And we always have this power here. So 2 to the 5th is 32. Then that, so 64 grains of wheat. And then on this last square here, there's 128 grains of wheat. And so on, so on. If you kept going, before you know it, the numbers become huge. Look, 2 to 17th is already 131,000 or more. 2 to 26th is already 67 million or more. All right, and we keep going. Look how big this number is. So by the 42nd square, we already have, what's this? Millions, billions, trillions of grains of wheat or rice. That's a lot. So the question was, how many is there on the 64th one? Well, I think you can see the pattern now, how you would find it. Just so you know, the total, if you added all the rice on the whole board, would be this giant number here. So that's a huge number. That's the total though. That's not how much is on the 64th one. So let's go back to how much is on the 64th one. So this is the same way our infection problem works. On day 1, we have here 2 people infected. On day 2, we have 2 squared, 4 people. So the same as we were just doing. And this first one of course, here would be 2 to the 0 power. All right, and here on day 3, we have 2 to the 3rd, 8 people infected. So notice day and power, and then it tells us how many people. So on day 64, how much is it? Well, on day 64, we would have 2 to the 64 people infected, which means this many here. All right, and that's the new infections, right, on day 64. That's the new infections, but then to find out the total number, you would have to find out adding all the days and all the people. So that's actually just the new infections on that day. Important to know. All right, notice here that every time we go from one term to the next term in the sequence, because we've created a sequence here, we're multiplying by 2. So in an arithmetic sequence, we're always adding the same number, but in a geometric sequence, we're always multiplying by the same number. Okay, so let's talk about that. Geometric sequences, you should add these notes in your notebook. We have a sequence with a common ratio between successive terms. So that multiplier between terms is called a common ratio. So here, to get from 40 to 20, we multiply by 0.5. Means a half. You multiply by a half. Then you multiply by a half again. So what are the other numbers? 5, 2.5, 1.25. The common multiplier can be found. Well, often we can just look at the two numbers and calculate in our head. But the way to do it is to take the second term divided by the first. So 20 divided by 40 will tell us 0.5, which is our common ratio. Or you could have done third term divided by second also. All right, next one. What's the common multiplier here? Or is there? There is. The common multiplier is multiplied by root 6. When you multiply 2 roots, you get the roots disappear and you have that. And then 6 times the square root of 6 is 6 root 6. And then this times the square root of 6, well, the 2 square roots cancel and you have 6 times 6, which is 36. So on and so on. So our common multiplier, you can take any two terms and divide. So this term divided by this term, that is actually the same as root 6. You could have done 6 root 6 divided by 6, which would give you root 6 as well. That's our common multiplier. Common ratio, geometric sequence. Geometric sequences. So here's another one. We begin with 3, it becomes 6. That means we multiplied by 2. And then 6 becomes 12, also multiplied by 2. Multiplying by 2 every time. Therefore, this is 48, 96, 192. This is a geometric sequence. You're always multiplying by the same number, and that number is 2. So the common multiplier is our ratio of 2. When you plot these points, if you plot these points here, position, number, and here's the term, watch what happens with our sequence. As you proceed through the terms, by term 6, it's rising faster. By term 7, it's going to be even bigger. So notice it's rising very quickly. It's not straight anymore. It's a curve. So geometric sequences are always what's called exponential. This is called exponential growth. It's not linear. It's not a line. It grows slowly and then quickens its pace. So that's important to know. Geometric sequences are exponential. Which are geometric? This one, yes or no? And what's the ratio? First one, multiplying by 3 every time. It's geometric, common ratio 3. Next one. Well, that's multiplied by 3.5, but this is multiplied by 1.7 to get 7 to 12. So no common ratio, not geometric. How about the last one? Okay, we're multiplying by 1/3 every time. Therefore, common ratio 1/3, it is geometric. Don't forget, to find the common ratio, we can always do the next term divided by the previous. This notation here means the next term divided by the previous one, right? So, for example, here we could have done 6 divided by 2 to get a common ratio of 3. Makes sense. Or we could have done 18 divided by 6 to get the same common ratio, so it works. How about the last one? To get the common ratio, we could have done 27 divided by 81, which reduces to 1/3, or 9 divided by 27, which also reduces to 1/3. Great. So sequences that have a common ratio or multiplier are called geometric. And we have this formula for finding the common ratio. Let's do some problems. Complete these sequences here and find the common ratio first. A, check your work. B, check your work. C, check your work there. In this one, we can find the common ratio like this to be a half, but now you need to go forward and backwards in time. What happens when you go backwards? Well, instead of multiplying a half like when you go forward, you actually multiply by 2, you double it. If it's becoming half going this way, then it's doubling going this way. So our numbers should be these, and then these two at the end here. Because a half of that is this, and then a half of this is this. Check the last one. Again, you're going to go backwards. You're going to find the common ratio, but then you're going to go backwards. Okay, there's our ratio of 5. Therefore, you're not multiplying by 5 in this direction, you're dividing by 5. So basically, it's like multiplying by 1/5. So notice here's our values here. So 1 becomes a 1/5, then you divide by 5, 1/25, divide by 5, and so on. Okay, let's go next one. Let's try this. We're going to make the rule for a geometric sequence. So here's a geometric sequence. We can see here we have a common multiplier of 0.5. Okay, so our ratio is 0.5. We're going to try the same approach we did with recursive rules. So let's make a rule for U2 using R and U1. Well, that rule can be to get U2, we begin at U1, and we multiply by the ratio like that. Okay, how about writing a recursive rule for U3 using R and U1? Check your work here. To get to U3, we begin at U1 and we multiply by R twice, right? To get to the third one, we go once, twice we multiply by R, so twice, this is R squared. All right, what about repeat for U4? What would that be? Here's your rule for that. This brings us to a common rule here, a general rule, UN. What would it look like for UN? And here it is. To get any term in the geometric sequence, we take the first term, multiply by the ratio, n minus 1 times. So this number is always 1 less than this number, and that's what this shows. There's our general rule. Important rule, there it is. Try it here. What is the general rule for this sequence? So take this and fill in the R value and fill in the U1 value, and then find the 8th term. Okay, here's our general rule. First term goes here, 24. We know it's geometric because it's half every time. So here's our ratio, our multiplier is half, n minus 1. So now if we need the 8th term, we put an 8 in here, we put an 8 up here, and we calculate this. That works out to this, and that gives us this value here. Okay, that's a very basic problem. Make sure you know how to do that. That's how basic these begin. All right, let's look at the next one. Try 1, A, B, and C. Okay, here's A, check your work. Here's B, check your work on that one. And C. Okay, 2 and 3 are a little different. Let's take a look at 2. Okay, in 2, it's told that she earns this much in her first year. In the second year, she's going to increase her salary by 5%. A lot of students make the mistake of multiplying 48,000 by 0.05. However, you need to think of it this way. We're multiplying by 1.05 because in the second year, she makes 100% of her original salary plus an additional 5%. That means now she's making 105% of her original salary, which means 1.05. So that's our multiplier. That's our R value. So in the 5th year, you'll take your first year value, you're using the formula, the UN formula, and you multiply by R to the 4th. There's her salary. Study this carefully. This is exactly the kind of problem you should understand and be able to solve from now on. Let's try problem 3. Okay, problem 3. I'm going to see if you can figure it out. I'm going to share the answer quickly. So check your work. We'll talk more about a problem like this tomorrow or next lesson. So take a look now, study it, see if you can understand what happened, but know that we'll come back to a problem like this soon. Here's the first part and here's the second part. Okay, another one. Let's talk about depreciation. Depreciation means you are losing money. So check it out. Instead of adding to 100%, we subtract. So we have a 92% multiplier, and there's our work for that one and that one. Check your work carefully. Let's try another one. Try this one and check your work.